We took a quick pause there. I had left my coffee out of the room and it was starting to show. I wasn't able to immediately recall what graphite was as far as a crystalline structure. It is hexagonal.
But it is not hexagonal close packed.
It is not hexagonal close packed. And one of the things that, like, as an aside, carbon has so many
Carbon
different
is one of
crystalline structures
Yeah.
associated with it.
I mean, because like it gets, and carbon is one of these atoms that, or is an element that shows up in all kinds of stuff.
Yeah,
But
we are carbon-based
yeah.
life forms.
Yeah, carbon-based life.
But carbon is, like you've got, buckyballs, you've got, which are spheroid
arrangements
of carbon atoms. There's carbon nanotubes. You've got graphene.
which is like a single atom thickness sheet that's
Yeah.
hexagonal, which is what graphite is essentially that stacked on top of itself.
Yeah, and then you have like amorphous
Yeah.
structures as well.
But that behavior of like these stacked sheets also directly corresponds to the behavior of graphite and why we use it in pencils. It
Yes.
it experiences a lot of slip.
A lot of slip along those planes.
So when you drag it across something, it peels off
Right.
very predictably.
Whereas this hexagonal close packed, that close packed of having that triangle in the middle
Yeah.
actually prevents a lot of slip from happening. And if you notice, magnesium, titanium, zinc, those are fairly brittle
Yeah.
metals.
They're very rigid metals. And
So we can start to see like some of the material characteristics that carry on up from just the like orientation of the atoms to one another in a crystalline lattice. All right,
we'll keep moving on.
keep moving on. Most diagram, and this is just the caveat that we gave earlier. They're drawn as though they are the same size, but they are not. The C arrangement, the body-centered cubic, is only the structural cell of that is not the same as the FCC, right? You like what it comes down to is that there's more atoms in the face-centered in a given repeating structure.
And that
that-
means that like an atom does take up a physical amount of space.
It's not it doesn't change size, like the atom itself doesn't change size.
but
Those structural cell, the units
Yeah.
that we were looking at do.
Yeah. And so a BCC, a body-centered cubic formation versus an FCC, the BBC or BCC, excuse me, is a smaller configuration. The FCC is a physically larger structure
Right.
when you compare them side by
When
side.
you compare them side by side. So metals such as iron,
Yeah.
chromium,
vanadium,
molybdenum,
all
tungsten.
these things.
These are body-centered cubic structures, and they have two properties in common: a high strength and a low ductility. Body-centered, again, body-centered, or the close packed, which also kind of has the same thing. That atom in the middle kind of stops a lot of the slip.
Yeah.
Whereas FCC metals are, which also includes iron.
Yeah, which also includes iron.
Notice we've got a completely different list of metals over here.
Yeah. This is also one of the things that's super nice about iron.
Yeah, it's super nice about iron, and that's why we use steels and why you can get to tease so many different material properties out of that, because iron is on both lists.
Yeah.
But you have in general on these, if we look at the rest of the list, you've got more ductile metals, like
Aluminum, copper.
silver, lead. Like these are kind of
These are metals that are easier to shape and form without them actually just completely breaking.
Yes.
They're much more prone to just bending rather than shattering.
And let's look at copper in particular. Like, where does ductile come from? It comes from the fact that you can like pull a wire through a die.
Yeah.
The ductile nature of copper is what allows us to form really nice thin wires out of it, because we're taking a larger piece of metal and we're pulling it through a smaller hole.
Yeah.
and that's how we get wire.
Yeah.
So copper, highly ductile, and that's
also
kind of,
highly ductile.
and the reason that it's able to go through that smaller hole is because it allows the atoms to slip past one another
Yeah.
on those slip planes.
Yeah. You cannot do this same process with like steel that's in its ferrite or iron that's in its ferrite configuration.
Yeah,
Like it will just break.
shear and break.
It'll snap,
Yeah.
essentially.
And then you've got beryllium, magnesium, zinc, cadmium, cobalt, thallium, zirconium. These are kind of all, again, harder, more brittle
Yeah,
structures.
these are the hexagonal close packed.
These are the hexagonal
close packed.
Yeah.
Not close. Close packed.
Yeah.
And again, these types of materials are like on the brittler side.
Yes.
And they can be very strong, but they fail in a
Yeah.
very particular way.
Yeah. So if we were to take a small section of a common metal, examine it in a microscope, you'd probably see something like this. And here we see just kind of these lumpy little things.
Clusters of,
And these are called grains,
yeah,
right? And so now we're zooming out even further.
yeah, we're at kind of like the next level.
So what is a grain? Is that like these are lumpier than what we see in the ordered pattern?
Yep.
Like, so is it, how do we actually get a grain? Go ahead and hit the next slide. Essentially, like a grain is a single continuous crystalline lattice. The dark lines that surround it are the grain boundaries. The grain structure refers to the arrangement of the grains within there, but each one of those is a single ordered crystalline lattice.
Yeah.
But as that crystal forms, it runs into other crystals that are not necessarily, like they could be the same material, they could be a different material, but the crystalline lattice, as it grows together, is not ordering itself in the same orientation. Like some of them are not in three-dimensional space aligned,
Yeah.
and so when they meet as solids, they form these grain boundaries.
And essentially, so the grain, where we see grain boundaries is when essentially there is if we're thinking about it in 2 dimensions, there is a directional change in the arrangement of the lattice.
Yes.
Right.
Yeah, and we'll see better on the next slide here. So this kind of zooms in on some of those grain boundaries, so you can see a lattice structure, and this is kind of like, just to make it simple, they use more of a just simple cubic structure. But these are meeting at different angles, and so as these crystals, like they just start off by a few atoms forming a lattice,
Yeah.
and then they kind of grow outwards, and this is happening as it solidifies.
Yeah.
And then it'll hit a wall there,
Yeah.
and then you get these grain boundaries.
And so like this is like these grain boundaries and these grains form, like if we took like iron, for example, from a molten state and we let it cool down, as it cooled, our atoms would be snapping into these different crystalline structures.
Yeah.
And then, but they are taking on a particular direction, and as more of these atoms kind of cluster together, they form into one direction, and you have another group of atoms that's forming into a separate direction, and they kind of butt into each other.
And they butt into each other. And one of the things that, like, crystalline structures you need to understand about, like, when they form, if you allow them to form very slowly, and this is true of amethyst, this is true of steels, if you allow them to form very slowly, you can the propagation of that crystalline lattice is likely to snap into fewer grains, fewer crystals.
You will get larger sections of continuous,
which is what you see when you see like amethysts. You'll see like, and why bigger crystals are more highly valued in general, like in gemstones and things like that. It's because the only way that they form those single crystals is if they're done very slowly. They cool down very slowly under the right conditions in order to make that single crystal structure.
Yeah.
So the average size of grain determines certain properties of the metal. And so we can tweak that by controlling the circumstances in which those crystals form.
Yeah.
The smaller the grain size increases this tensile strength and tends to increase ductility. Larger grain size is preferred for higher temperature creep applications. So that creep is basically like deformation that increases with time or under a constant load or stress.
Yeah.
So, for instance, there's a meticulous process that's undergone to create the turbine blades in a jet engine.
Right.
To create a single crystal lattice, even though it's in the shape of a blade.
Yeah.
Essentially, what it is like the external part of the crystal is a grain boundary and it has a shape to it, but like internally, it's all one crystal.
Yeah.
And they do that because of that high temperature creep
Yeah.
issue, so that it does not have that.
Yeah. And this is like it's not easy to do that.
It's not.
And so that's part of the reason why, like, you look at a component for like a turbine blade, and then it's this little piece of metal that might be just a couple inches wide, and it's like, you know, maybe a couple millimeters thick or something like that, and yet it costs thousands of dollars to manufacture.
Yeah, and it's because they have to like control the temperature, atmosphere, all of that for a long period of time in order to get it to exhibit the material problems.
To get that continuous crystalline lattice.
Yeah.
To that size. So it's a very finicky process. So like when we like these types of things, like again though, it's like you can see that like we're pulling like the fundamental properties of like an individual element or atom, the way it arranges itself, like as like we pull that up to the macro scale, and we're doing it because there's a particular material property that we want out of that material.
Yeah, we're tweaking it.
Yeah.
We're tweaking it by like changing how we process and mix it.
Yeah.
Yeah. So when we quench a metal, the grain size and grain patterns are controlled. Grain characteristics are controlled to produce different levels of hardness and tensile strength. Generally, the faster a metal is cooled, smaller the grain size will be.
Yeah.
But there's other things that can happen.
Yeah.
Right? And so when we really get into the steel heat treatment thing, when you're dealing with steel, it isn't just that it's changing that, because we would also see a greater ductility with that heat treatment change.
Yeah.
The difference is that with steel, it will make it harder. Sometimes when you quench it, it will like some metals, you quench it, it makes it softer.
Yeah.
And the reason is that we're saving, like when we quench steel in particular, we're saving a much more brittle crystalline structure.
Yeah.
Our body-centered cubic.
Yeah.
And we're
minimizing
the face-centered.
The face-centered cubic. So we are emphasizing the ferrite formation of iron and in that.
Yeah.
In that structure.
So, and we'll get into all of that.
We'll get into all of that. Yeah.
In a little bit here.
So.
So grain, like obviously the problem is they're meeting up and they're not having the same thing. Grain orientation also has an important property characteristic. So depending on how our metal was formed, there's either a random arrangement of grains, such that no one direction is prevalent over another, but then you can have them aligned. And like things like hot rolling processes would achieve this sort of alignment.
Yeah.
Which gives metal a better tensile strength in one direction.
Yeah, and so like this is, again, we do this because we're looking to augment or tweak the material properties of any particular metal. And you know, the hot rolling process, that works for iron and steels very commonly, but it doesn't work for every material. And so if we needed to align the grain structure of, you know, maybe another metal like copper or something like that, it could potentially be a different process that you have to go through to do that alignment.
Yeah. So we often call this this oriented in the same direction thing the preferred one. It's not necessarily preferable in all situations.
Yeah, sometimes the other arrangement is desirable.
One of the things I want to point out here is we talk about materials in general as to whether or not they're isotropic in nature or anisotropic in nature or even quasi-isotropic in nature. So isotropic, if you hear us throw that term out there, it just means the same strength in all directions.
Yeah.
Anisotropic means that it has a singular direction that it is stronger in.
Yeah.
Quasi-isotropic means that there's essentially certain directions that it's stronger in.
Yeah.
And so the difference here is that we have traded off strength in all, like in that preferred orientation where they're all aligned, we've traded off strength in one direction for strength in another. So that is anisotropic as opposed to isotropic on the left.
Yeah. And so, I'm sure people can think of potential scenarios where you would perhaps want an isotropic arrangement of grains for.
If you're going to be loading it from all directions, then you're going to want that.
Preferable grain arrangement.
Yeah, but if you're only loading it from one direction, yeah, sure, you'd like to have all of those aligned.
Yeah.
So now we get into something that, like we talk about imperfections. And it's important to understand that imperfections lend material properties to things that may be desirable too. So like thinking about this as a judgment call is not true.
And imperfections is kind of like a loaded word.
Yeah.
So it's but it's the word that we use when we're in material.
I mean, it's imperfections if you're looking at things from a particularly fascistic viewpoint, like all these soldiers are not in alignment.
Yeah.
And that's what it is. It's like, the crystalline structure has little problems in it.
Yeah.
So we're going to talk about all of those different types. We can divide these into 3 categories, and then we can subdivide those even a little bit more. And so we'll talk about these. Point imperfections have atomic dimensions. Line imperfections are many atoms in length, and interfacial imperfections are generally many atoms in length. So let's start with the smallest of these. We're going to talk about point imperfections. So hit the next slide. We'll have a visual here of the crystalline structure here. A vacancy is where, in this sort of body-centered cubic structure, we have an atom that's missing in it. And you can see that kind of causes the sides to kind of warp inwards.
Essentially a void. And
Yeah.
So like the actual geometric arrangement of the atoms at this particular location is not optimal given the crystalline structure that is the rest of the surrounding area.
Yeah. Well, it doesn't conform to the repeating pattern.
It doesn't conform to the repeating pattern.
There's reasons why we do these things. There are reasons why we do this on purpose, right? So substitutional is where we have a different atom in the middle.
Yep.
And we do that on purpose in semiconductors.
Yeah, we specifically do this to get a particular material property out of semiconductors.
Yeah.
Semiconductors do not semiconduct unless we do this to them.
Yes. So, do keep in mind, like, we're talking about these, they're imperfections. They're only imperfections if you like all your soldiers lined up exactly how you want them.
Like, I think maybe perhaps a helpful, correct me if I'm wrong, perhaps a helpful way to think about this would be, it's like, this is kind of like a question of like purity or uniformity.
Yeah.
When we talk about imperfections in this way, like when we're talking about imperfections in material science, it's like uniformity of the material is really what we're saying. Is like it's not uniform.
Yes.
That's not necessarily bad.
Which is why I said it's a particularly fascistic way of looking at it.
Yeah, like it is really important to understand when we say imperfections, in many times imperfections are highly desirable for particular applications.
Yes.
So these are not flaws in the material
it is
itself.
not garbage.
Yeah.
Right.
Yeah.
In fact, it's very desirable. Like particularly with the example of semiconductors, which is a substitutional imperfection that allows us to switch electricity on demand.
Yeah.
Which fantastic thing. Interstitial is where we have one extra in a position.
Yeah.
So those are the 3 basically. You can have one, too many. You can have
missing one.
You could have something different, or we could have too many in that position.
Yeah.
Yeah.
And so, like, the actual geometric arrangement of the atoms at this particular location is not optimal given the crystalline structure that is the rest of the surrounding area.
So So there we go.
Yeah. I think we just kind of talked.
We kind of talked about each of these, but these are there for you to go through on your own. So we skip through these. Now we can talk about
Like,
interstitial defects. Oh, we already talked about that one too.
Yeah,
That one just looks a
interstitial.
little different. So line imperfections. Line imperfections pretty much start as a point imperfection and then they propagate.
Yeah.
Sometimes you can wholly contain a point imperfection, but sometimes they propagate out into a line. And so you can have edge type, screw type, or mixed type that basically is to, like the edge type is just a linear one, whereas a screw type tends to jump in a third axis
Yeah, so like
and screw around a.
like it kind of creates like almost like if we were to look at it, we have a screw example in the bottom right here. If we were to like continue that out, it would kind of like create this spiraling stair step effect.
Yeah.
If we were to do multiple levels of that.
And so we're talking about a line that's being formed. So it begins this one, the edge location that you see there. It begins with a point imperfection,
Yeah.
an interstitial one, and then it continues on and forms that line,
Yeah.
dislocation between a perfect lattice structure,
Right.
our pure one.
But, yeah.
So line imperfections kind of propagate. This shows you forces that happen. We create line imperfections every single time we subject a metal to shear and actually deform it.
Yeah.
And so this shows you kind of the transfer of those line imperfections as it goes through. And then eventually, like if you shear it enough in one direction, you will snap it back
Into like another.
into another continuous one, right? We haven't introduced, like unlike a substitution, right?
Yeah.
We haven't introduced a different chemical into
Yeah.
it.
And just to be clear, when we're looking at this diagram, the arrows represent forces.
Yeah, the arrows represent forces. Thank you for
Yeah.
clarifying.
So that's where we're applying force to the structure, and so you can see that as we move through this, like it's deforming in relation to where those forces are.
And you can see where those dislocations kind of shift their way through that crystalline structure so that eventually we wind back with the same crystalline structure if we apply the pressure enough.
Enough. Yeah.
So, then we have interfacial. So like if you think about it, we've kind of gone through the evolution of geometry here. We've gone between point to a line, which is like 2 points.
Yeah.
Or many points.
Yeah.
And then interfacial is kind of like a plane,
Yeah.
right? So they exist at an angle between two faces of a crystal or a crystalline form. So they form the outer edges
Yeah.
of whatever solid it is.
Yeah.
It tends to be an interfacial imperfection unless it is a perfect single crystal
Yeah.
that is formed naturally without anything bounding its geometry.
Yeah.
But those turbine blades, the entire surface that we were talking about, because they don't conform to the crystalline structure,
Yeah.
those are entirely interfacial
Yeah.
imperfections. They're just all on the outside of it.
Yeah.
Internally, it has none.
And I think in reality, like if we're thinking about like this idea of like growing a crystal like in an unbounded space with nothing interacting with that, like that doesn't really happen outside of like lab conditions when we're growing crystals in like
Or a geode.
or a geode.
Because
like,
you think of a geode, that has the space inside
and it can grow
in towards the interior.
Yeah.
So yeah, but like, because most things are doing that in a confined space,
Yeah.
you know, like when we talk about those things, that's how, like, grain boundaries are interfacial imperfections.
Yeah.
So we talked about grain boundaries before. Now we've kind of got a better definition of what they are.
Yeah. And they happen like all the time.
Yeah. And it's important to note, like, they're there and they help us with certain things.
Yeah.
They give us certain properties out of the metal.
Yeah. And we can change and we can mess around with them to enhance particular properties of metals and other materials when we're working with them.
Yeah. So dislocations can't necessarily end inside the crystal. They almost always lead to, like, propagate out to a grain boundary.
Yeah.
So like oftentimes like point imperfections almost always like they,
Result in a line imperfection that
Yeah.
traverses out to the perimeter of a grain boundary, or,
yeah,
or a
facial interfacial.
facial imperfection.
Yeah. All right, we're going to take a break here because now we've kind of done our zoom in real tight and then slowly pan out of what the materials are, how materials are formed. Next, we're going to talk about iron and carbon alloys, or steel as we like to
Yeah.
call it, in the next video. So we'll leave you there. Again, with these videos, please rewind, watch, and then also use the slide deck.
Yeah.
Pull it up separately. Make sure you understand things on them. And particularly in the next one,
There's going to be a lot of stuff that we intentionally skip over.
yeah, so that we don't have talk at you forever and ever and ever.
So we'll see you guys in the
We'll
next
see you in the
video.
next video.